And then I'm going to go ahead and share my screen. Can everybody see that all right? Okay. So last time we started partial fractions, right? We discussed the different types that you could have between linear, quadratic, and distinct and repeated. And there's this nice long drawn out example for you in the notes already. And then I went through and completed this first problem for you, right? And I believe that I then split you guys up and let you try B. Is that right? Would you like me to quickly go over that one?
Yes, please.
Okay. So the very first thing you have to do for these is factor. So I would rewrite this as this to start. Actually, no, hold on. I could take out two x's. So I would take out an x squared, and that would leave me behind x plus 2. These are both linear. Don't let that x squared fool you. If it was x squared plus 5 inside parentheses, something like that, that's a quadratic term. If it's x squared by itself, that is a linear term. And that's also a repeated term. So when I write this out, I need a over x plus b. I go up a power to x squared. That takes care of the x squared linear repeated term. And then for the last part, I need, and so I'm going to use d instead, just so that, at the end of the problem, we always put plus c. And those two, that c that I have there and the plus c at the end aren't the same thing. So let's just skip it and not have to worry about that confusion. So I'll put d over x plus 2. All right, so that's the breakdown. Now I need to get a common denominator. And I know that when I was jumping in and out of the groups, remember one of the things I said to you kind of jokingly was don't reinvent the wheel. Right, so the common denominator you've created, it's right here. So the a term needs another x, and it needs an x plus 2 in it. The b term already has x squared in the denominator, so it just needs to be multiplied by x plus 2. And finally, the d term already has the x plus 2, so it just needs to be multiplied by x squared. And all of that has to equal the original numerator, which is 2. So all I did was I skipped the step where I wrote out the denominators. They're all going to be equal if I do it correctly, and they're all going to cancel. So I don't really need to put them. But of course, until you get comfortable with it, you might want to keep doing it. So multiply this all out. I have ax squared plus 2ax plus bx plus 2b plus dx squared, all equaling 2. Put all the x squared terms together. That looks like a plus d, where I got x squared there and x squared there. There are no x squareds on the right-hand side, so this is 0. X terms, I have 2a plus b. Again, there are no x terms on the right-hand side. If you want, you could write 0x squared plus 0x, if that helps you. And so this is also must sum to 0. And finally, we have 2b left, and that must equal 2. So that right off the bat tells me b equals 1. If b is 1, then a up here is equal to negative b over 2. And then finally, if a, or this last equation here tells me that a has to equal the opposite of d or vice versa. So d equals the opposite of a. So d has to be 1/2. Good so far? So now we just need to plug those three things back into this integral. So negative 1/2 integral dx over x, that's the a term. Then b is 1, so that's going to be 1 over x squared. And I'll just put dx up there. And then finally, d is 1/2. And that term should have been over x plus 2. So each one of these are fairly simple. This one and this one, hopefully you can identify as natural logs fairly quickly. The one in the middle is not. People want to just assume that all of them are always natural logs because most of them are. I'm going to rewrite that one as x to the negative 2 dx. And then hopefully you can see that it's not a natural log. So you should end up with 1/2 natural log x. Now this one, you add 1 to the power, makes it -1, divide by that number. And then the last one is also a natural log, which you could find by a simple u substitution, and it is x plus 2. Finally, all plus c. And then I'm just going to do a little bit of simplification. There's nothing wrong with what we have here. I might write, instead of divide by -1, write this whole term as -1 over x. Right, the -1 power means put it in the denominator, and it's divide by a negative number, which same thing as negative. So I noticed that this has a 1/2 power and this has a 1/2 power. So you may recall there's a rule of logarithms that say if I have a constant in front, then I can rewrite it as the log of the inside to that power. So I'm going to say that that 1/2, that's the same thing as a square root if I were to use it as a power. So this is going to be minus the natural log of the square root. And then this one's going to be natural log square root x plus 2. And the reason I did that is because now I can put these two logs together. There's another rule that says the natural log of A minus the natural log of B is the natural log of A over B. And so I can rewrite that as natural log square root absolute value that could be plus C in there. So just a little cleaner and just kind of a review of concepts, not a major step.
No, the little thing, say for the post note we're allowed to have on test, and you wrote down ln a minus ln b equals ln a over b. Can we have that on the postcard?
Yeah, you can write that down.
Okay.
That's just a formula.
All right, cool.
So any questions about that problem before I move on? Keep in mind, I can only see a few of you. Like, personally, I can only see a few of your faces, but it only allows me to see 5 people at a time. So if you're, shaking your head or nodding or something like that from time to time, I won't see you. All right.
Does it matter that you use the letter D instead of C?
I chose D at the beginning of the problem because we have this plus C that we introduce all the time. So
Oh, yeah.
to avoid confusion that C and the other C are not the same quantity, I just skipped it.
Okay.
All right, so this is another example. I think we have maybe 2 more here. Yeah. So I think maybe, let's see, which one of these do I want to do? Guess maybe I'll do D here. And then I'll let you guys try the other one quickly. Unless, of course, you feel comfortable enough to try the other 2. You'll have to let me know. Would you guys prefer to try more on your own or me do one more?
I prefer if you show us how to do the problems, and then if we could try it in group time or on our own time with the homework.
Well, I'm going to give you a chance to do it as a group. I'm asking, would you prefer to have 2 problems to do as a group or just one?
One.
Just one.
Okay. So like I said, I think I'll do D then, and I'll leave C for you. All right. So what looks different here? Why is this problem more challenging?
There's something in the numerator.
There's something a little different up there. So it's going to change how we solve. What about the denominator, right? The first thing we have to do is to factor, right? We're typically used to factoring x squared as our highest polynomial. We could still factor this. If you don't like the way it looks, I would suggest letting maybe u equal x squared. That means that u squared is x to the fourth. Now, I'm not making a u substitution. I'm just doing this for factoring purposes. So you can call it whatever variable you like. So actually, let me just pick something else. Let's do z. So if I rewrite the denominator, it now looks like z squared plus 3z minus 4. That looks a little more familiar. So now I'm looking for two numbers that multiply to -4 and add to 3. What are those numbers?
4 and -1.
Okay. So this is z plus 4, z minus 1, right? Then, of course, we're not dealing with z, we're dealing with x, so let's replace it now. So this is x squared plus 4, x squared minus 1. You should take it one step further because x squared minus 1 is the difference of two perfect squares, which means it can factor once more as x minus 1, x plus 1. Remember, it always factors as a plus b, a minus b. Anybody remember what that set of factors is called?
Conjugate?
It's conjugate pair. Good. All right, so that's my factored form. So my integral now is going to be x plus 3 over these three factors. I notice this here doesn't even have a dx on the sheet. All right, so now that we've factored, let me just go ahead and get rid of this because I no longer need it. Okay. This then we have to break into some constants over top of the pieces. So x squared plus 4, what kind of factor is that? So is it linear or quadratic? And is it distinct or repeated?
Is it a quadratic distinct?
It is a quadratic term because it's x squared plus something else, or it could be minus, right? It could be either. And it's also distinct because it's not, or it's to the first power outside of the parentheses. So that means we need an ax plus b over top of that term. That's the correct format for a quadratic term. And then over the x minus 1, x plus 1 terms, we need a single constant. I'm going to use d and e again to skip the c. So d over x minus 1 and e over x plus 1. Okay.
Now, in this case, so it's the reason why x squared plus 4 gets a and b is because x is squared.
It's because it's x squared plus something else. If it was just x squared, then you would use that as a repeated linear factor, which we just did in the last example.
Okay, but even though like for D and E, even though you're subtracting and adding 1, that doesn't necessarily count.
What do you mean doesn't count?
So say, since we're adding and subtracting something in say x1,
Oh, from
that
x. Okay.
that only has the letter D instead of having like say D over D E over x minus 1.
But that is because it's an x to the first power, not x squared.
Okay, I got you.
So basically it's, is this the equation of a line, which it is, and then is this the equation for a quadratic? The only thing that doesn't work for that is if you have something like x squared. That is a quadratic, however, it's not one that's got any b and c terms, right? You have bx plus c typically. That's the only one that doesn't follow that pattern, because that's actually a repeated linear.
Okay.
All right. So now we need to get the common denominator. Again, we've already found it. It's this factored form. So the ax plus b term is missing x minus 1, x plus 1. So multiply it by both of those. The d term is missing x squared plus 4 and x plus 1. And the e term is missing x squared plus 4 and x minus 1. And all of this has to equal the numerator, which is x plus 3. Everybody okay with that line?
Yeah.
All right. So now we've got to either try the elimination method or the system of equations. I think I can demonstrate to you why I'm not a huge fan of elimination in this problem. So I'm going to try it here. Let x equal 1. If I do that, that will eliminate this term because that'll become 0. And it'll eliminate that term. So I will get d times 1 squared plus 4 times 1 plus 1 equals 1 plus 3, right? Everywhere I see x, I have to plug in 1. So this is 5 times 2 or 10 is equal to 4. Looks like this is going to be 2/5. All right, not bad. That was easy. How would I eliminate the x plus 1 term?
Let x equal -1.
Okay. My is not erasing. Go away. No. There we go. All right. So now let x equal -1. So that term right there goes to 0. That term right there goes to 0. Right, because 1 plus -1 is 0. Then we have e times -1 squared plus 4. -1 minus 1. -1 plus 3. Okay. So this is going to be 5 times -2 right? And over here it's going to be 2. So it looks like minus 1/5. All right, great, not so bad. Here's where it's a problem. There are 2 terms that have x squared plus 4 in it. Is there any number of x I can plug in there to make x squared plus 4 equal 0?
No.
It would have to be a complex number, right? And we don't deal with that sort of stuff in our basic calc classes. So instead, we just have to pick some arbitrary x value. So I'm going to let x equal 0. So now if I go through all of that line there and plug x equals 0 in everywhere, let's see what happens. So I got to simplify all that. So this is 0. And then I've got -1 times 1 times b. So I got negative b. And then I'm going to have 4 times 1 times d. And then 4 times -1 times e. All equaling 3. Did you guys follow that? So then, let's see, we have d and e, which means we can solve this for b. So it'd be 3 minus 4d plus 4e, but then that negative sign on the b would flip everything. And plugging in. It's like minus 3/5. So now we've got B, D, and E. But guess what?
Stop.
Okay, let me know when I can continue.
I'm sorry. He was pushing buttons.
So do you guys see why I'm not a huge fan of the elimination method so far? Right, it's not terrible. It's just a lot of got to make a lot of smart choices. Let's see. Maybe I'll just look what A was real quick. If I can find my notes here. I don't know what I did with them. And I can check the others as well. Here we go. My luck, I probably didn't write this one down. All right, looks like A turns out to be minus 1/5. So just to save us some time. Yeah, I think we've done enough of the algebra to know how to do it. Let me see if I can. There we go. An extra page. All right. Oop. Guess it put it above the stuff. Fantastic. All right, so let me grab this guy. If it'll let me. There we go. Okay. So A was -1/5. B was why not see it on my page here? B was -3/5. C and D. All right, C. Oh, sorry, D and E, 2/5 and -1/5. Before I had B was 1. So let me just check these calculations real fast. Might even just quickly do the other method just to make sure. Rather be correct than just stick with whatever's there. Come on. So just bear with me for a second and I'll check these. Let me delete all this stuff. All right. So let's see, this would be A x cubed minus ax squared. Actually, let's do this. Ax cubed minus ax squared plus bx squared minus b dx cubed dx squared all right. Cube terms. squared terms. So we got an extra term there. Yeah, this term is screwed up here. Ax cubed minus ax. There we go. Losing it. Gotta get used to switching between the pen and the cursor. Okay. Come on. All right, so we got the x squared, so we need x's. So we've got minus a plus 4d plus 4e. Now there is an x term on the other side, so that's got to be its coefficient, which is 1. And then constant terms, we've got minus b plus 4d minus 4a. Or e, sorry. So then that's going to be the 3, right? Because that has to equal the constant term. All right, so now can we get these down even further? Looks like if we add these two and these two, we can get down to 3 variables. Actually, I think we're going to want to do these two equations. Notice they have the exact same variables, a, d, e. D and E are both positive for both. So if I were to multiply that first equation by a -4, and add it to the third equation, I would get -5a. The D's and E's would cancel out completely, and I would get a is minus 1/5, right? So that was 4 times equation 1 plus equation 3. Then I'm going to do, let's see, equation 2 and 4 look very similar. They have all the same stuff. If I multiply equation 2 by 4, and subtract equation 4, so 4b minus a negative, that would be 5b. 4d minus 4d would cancel. Negative 4e minus a negative 4e would cancel. And 0 minus 3 is minus 3. Giving me b is -3/5. So it looks like everything's going to work out for us, right? It's like A, B, C, and D are all looking the same so far. So let's just finish this up quickly and then give you guys a chance to try those. So I've got A and B. Let's see. Now if I take equation 1 and equation 2 and add them together, that would give me A plus B plus 2D is 0. We know A and B already, so we can solve for D. Comes out as 2/5. And then finally do the same thing with the last two equations. So if you just add equation 3 and 4, and solve for D, or sorry, actually, hold on. We already have D, so I guess we want to, let's subtract the 2. That'll get it for us. So do 3 minus 4, 4 minus 3, whatever you prefer. Solve for E. Let's see, 12. Do that right in my head. Wait, this is negative. All right, so let's check that then. So A was 1/5. Negative 1/5, sorry. B is negative 3/5. D is 2/5, and E is negative 1/5. All right, fantastic. So those are all good. Whew. All the algebra's done. We can finally do some calculus. So integrate. I have AX. A is negative 1/5. B is negative 3/5 all over x squared plus 4. D is 2/5. And E is negative 1/5. Okay. So break all of these up. So this is going to be minus 1/5. And minus 3/5. 2/5 and negative 1/5. So I really just took that first integral and split into two. And I do that because the first, third, and fourth integrals are all natural logs. This one right here is the only one that's a troublemaker. And I could tell that because for this one, if I let u equal x squared plus 4, du is going to be 2x dx. So I'd put a 2 in, put a 1/2 outside, and that's going to give me du over u, which is a natural log. This one right here is going to give me natural log x minus 1. And this last one, natural log, oops, I'll put x minus 1 twice. Should be x plus 1. There we go. X plus 1. And then plus c. We just got to figure out what to do with this one here in the middle. Now, I could be really rude and say, go ahead and do that as a trig substitution, right? Because that is technically how you would solve that. Remember, I told you there were cases you could use it where there weren't square roots. However, that is a form that you may or may not recognize. So can someone go back to their notes for me? The very first packet of notes that I gave you that had the basic integrals in it, and tell me if you see one that has 1 over x squared plus 4 in it.
There's only one that has 1 over x squared plus 1.
Okay. And what's that one?
Its antiderivative is arctangent times x.
Okay. So what do we think this one's going to be?
Would it be arctangent x plus 4?
So remember when we made our substitutions, if we let x equal something, that other term is a squared. And where does that go once we were done?
Would it go out in front?
So I'm going to do this one on Mathematica real quick for us, see if it comes out nicely. It hasn't loaded yet. Okay. So can everybody see the Mathematica page now?
Yeah.
All right.
Yes.
I'm going to do this integral on here just to save us again some time, but certainly something you could do to practice. It is 1 over x squared plus 4, integrating with respect to x. So it comes out as 1/2 arctan x over 2. So that would be minus 3/5 times 1/2 arctan x over 2. So I know that that was a very long, intense problem. My answer's super long. And I'm guessing you didn't really like the explanation of the arctan, but I was just trying to save you some time and brain power there. So any questions that I can answer for you? Where did you jump off the rails? So everybody understood that perfectly then. You could recreate it right now. I'm going to go ahead and give you 15 minutes to try this problem, because I would like to get to the other topic for today. These problems are quite time consuming, unfortunately, especially when you double check your coefficients and all those things. So I'm going to go ahead and break you guys into groups. And I will be jumping in and out, asking questions and seeing how you're doing. So the problem was cosine over sine cubed plus sine. Let's see. All right, so there's your breakout rooms. All right, any questions about the problem that I just gave you?
Yeah, so I know this is probably like stupid. But so what I did that I got like my mistake was like I guess I should have split it up as the negative u over u squared plus 1 and then 0 over that. But I tried to pull that negative u plus 0 out to the side because I thought I was supposed to do the arctan, like because I saw the u squared plus 1.
Mm-hmm.
So why shouldn't I have done that?
So when you say you pulled it out to the side, you mean you put the u out in front of the integral?
No, like because the one was over the other, I pulled it out as like how I would pull out a constant.
That's
And
what I
then I
meant.
turned it, yeah, I turned it into like 1, so it was 1 over u squared plus 1, and then it was just negative u plus 0. And then I turned them into like, I split them into separate integrals so that I could get arctan of u, and then, do you want me to show you?
Yeah, that would help.
Okay, hold on. Like,
Let me just make your screen a little bit bigger here if I can do that.
yeah, so we're looking right here. I split it up that way.
Okay, so 2 steps above your finger up here at the integral,
There?
there are 2 separate integrals there. There's 1
Yeah.
over u, and you're missing
Right.
a u there, by the way. You should have a
Okay.
1 over u du, which results in the natural log of sine.
Right.
Then you have minus u over u squared plus 1.
Right. And that's where I made my mistake.
Okay, so or put that back up real quick. So I don't know where you got this extra minus u term.
That
okay,
right
hold on.
there.
Oh yeah, that does you can't break that up. You're not
Okay.
allowed to take the u on the top and put it in a separate integral. That's all one integral.
Okay. Yeah, that's where I made a mistake. I was just like, I split the top from the bottom and turned it into arctan. So,
Yeah, you can only split up integrals if it's, plus and minus terms. You can't take fractions and split them apart. You can't.
okay.
One thing I see a lot of people do is if you have something like cosine times sine, they'll try and make it integral of cosine plus or times integral of sine, neither of which is correct.
I guess I was thinking about it as it was like negative u plus 0 times 1 over u squared plus 1. That's how I thought about it. And that's why I tried to pull them apart.
It is effectively that, but you still can't pull it apart.
Okay. So just, okay.
I think you got caught up in the problem that I did with the arctan and just saw that squared term plus a number and just automatically thought arctan. But in that case, it's actually a u substitution.
Right. Okay. Yeah, that makes sense. Okay. Thank you.
Mm-hmm. All right, so now why can't I made your video big so that I could see what you're putting up, and now it's still big. Try that button. There we go. Now I see everybody. All right. So let me go ahead and share the next section of notes. All right, so I'm going to take about hopefully 20 minutes to do this first part. These approximations are by no means difficult. They are what I would like to call tedious. So they're just kind of a pain to calculate. But in terms of calculus, there's not a ton that we're about to do. So far through this class, everything we've done has been a technique to solve integrals. And we've seen all kinds of things, right? We've seen u substitution, integration by parts, partial fractions, trig substitution, trig integrals, tons of stuff. But there are plenty of integrals that do not fall into those categories. So therefore, we don't know how to solve them with our current bag of tools that we have so far. So the next best thing is we can do an approximation. And in fact, if you are to ask a computer program such as Mathematica or your calculator to integrate a definite integral for you, it will use one of these methods. So the very first method pictured here is the thing that we've always used, which is the midpoint rule, or more effectively, we called that our Riemann sum. So we said that we could translate the definite integral into this summation of the areas of these little rectangles. So n here is the number of rectangles or number of objects that we're using the area of. A and B are the bounds on my integral. Delta x is the thickness or the width of one of my rectangles. X sub I is the midpoint of those rectangles. And then we know that the area is x times the function at x. Right? The function at x gives us the height. So the width times height is going to give us the area. But of course, we've already done that. So we want to learn two new methods. The other two are called the trapezoidal and Simpson's rule. Trapezoidal is really nice because it uses trapezoids. Right? The name and the shape coincide. Simpson's rule, I guess the gentleman that created it was, really wanted his name stamped on it. I would prefer if it was called the parabolic rule because it uses parabolas. I mean, if I invented a formula, I'd probably want my name on it too, let's be honest. Now, the method is approximately the same. We're still looking for the area of these shapes, but our formula looks a little different. So we still have to calculate delta x. The only difference now is, notice for trapezoidal rule, it's called T sub n. So I'll tell you now, and then you'll still question me when it's time for a test. I'll say on the test, calculate T sub n, or say T sub 8, for instance. So that means that you're going to use trapezoidal rule, 8 trapezoids, right? N is 8. So you would calculate delta x. Trapezoidal rule has divide by 2 out front. Notice Simpson's rule has the exact same coefficient of delta x, but it's divide by 3. Okay, so that's one difference between the two methods. The other difference is the coefficients inside. Now they both have it such that the first and last terms have a coefficient of 1. For the trapezoidal rule, all of the terms in the middle have a coefficient of 2. So notice it's f evaluated at the first point plus 2 times f evaluated at the second plus 2 of f evaluated at the third, and so on. And then the last one has a coefficient of 1. Simpson's rule is close to that. It again starts with a coefficient of 1, then goes to 4, and alternates 2, 4, 2, 4, until you get to the very end, and it's a 1. So notice the second term has a coefficient of 4, and the second to last term has a coefficient of 4. If you don't have that, you haven't picked the right number of points. All right, so let's try one. We've got our formulas. So this says, consider the area bound by the function sine x over x between 1 and 3 and the x-axis. So first it says, graph the above area and construct a definite integral. So again, I'm going to enlist the help of Mathematica to get a nice pretty graph. You are more than welcome to plot this on your calculator. Make sure you're in radian mode when you do so.
Did you just say degree mode, right?
You should be in radian mode.
Radian. Okay, sorry, I didn't hear you. Thanks.
Just share this really quickly. Okay, so there is my plot of sine of x over x. But I really just want the piece from 1 to 3. So when I shrink it down, it's going to get a lot less eventful. When I look at just that piece, that's from 1 to 3. Now, of course, this is The scale isn't the same on both sides. Mathematica automatically does that for you, so it almost looks like a straight line, right? But if we zoom back out again, from 1 to 3, it is obviously not straight. Looks pretty close, but not straight. So that is the area, right, from here over to here that we're trying to calculate. So before I do this, let me ask, do you think a trapezoid is going to fit this best? Or do you think a parabola is going to fit it best?
Parabola.
Okay, so let's calculate this and see what happens. So we've got our, do our graph here. Okay, so it's 1 to 3, something like that. It said construct a definite integral. Well, we would be integrating sine x over x with respect to x from 1 to 3. So again, let me say this to you. Looking at that integral, what method have we learned so far that would allow you to solve it?
And separate.
I think by parts is probably the only way you could solve this problem. And it would be quite ugly, I think. So let's go ahead and use these methods. So it says first it wants us to use our calculator to get an approximate number. So does everybody remember that I told you how to do the FNINT function? You go to math, option 9, and you should see this, depending on how old your calculator is. So we're integrating from 1 to 3. We're doing sine of x divided by x with respect to x. So I have that all typed in now. And when I run that, I get approximately 0.90256945576. So we will take that as the correct answer. Now it asks us to use the trapezoidal rule. So trapezoidal rule, n equal 8. So first off, we need to find delta x. That's b minus a over n. B is equal to 3, a is equal to 1, and n is equal to 8. Those are the bounds, and then the number of trapezoids that we're using. So we have 1/4 for delta x. Then we can go ahead and find the endpoints, right? Those values up here of x0, x1, x2. We need to calculate those. Well, the first endpoint is 1, right? Because that's where we start our integral. And if delta x is the thickness, then the next endpoint is 1/4 away from that particular spot. So 1 1/4, or 5/4. And I'll just keep counting up by 1/4 until I get to 3. Let me just move this guy out of the way so I can put this over here. So one way to know that you've done this correctly, n was 8, which means you should have n plus 1 endpoints. So in this case, we should have 9 of them. So let's see. And as I count, I'm going to simplify these if possible. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, that's good. So I have all my endpoints. So these are my values x0, x1, x2, and so on that I'm going to be plugging in. So I'm doing the trapezoidal rule first. So t sub 8 is approximately equal to delta x. Ooh, what am I doing? Delta x over n. I'm sorry, over 3. No, 2. Dang. Look up here. Delta x over 2. Then I have f of x0. Then I start doing 2 times. That'll be x sub n. Okay. So let's plug in. So delta x was 1/4 divided by 2. Now the question is, what is f? Well, that's the function that's inside the integral. So for each one of these, I need to calculate sine over the value. So the first one's going to be sine of 1 over 1. Right, sine x over x. Plus 2 times sine. My next value that I have is 5/4 divided by 5/4. Then I'm going to do 2 times the next one. That's sine of 3/2 divided by 3/2. I'm just going to go ahead and write the rest of them. And then finally, the last one has a coefficient of 1. Whew. All right. So again, nothing I've done so far was a hard calculation. I've done basically no calculus. And yet this is the hardest part. Now you have to type this into your calculator. I would suggest calculating one piece at a time and writing it down out to as many digits as possible and then adding it all up, or calculating a piece, storing it in the calculator, then calculating another, and so on. So I'm going to quickly show you how to store a value. Again, make sure your mode is in radian mode, or otherwise your efforts will be for nothing. So the first one was sine of 1 divided by 1, right? So I'm just going to do sine 1. Don't need to divide by 1, that'd be silly. I get 0.84 or something, okay? Now, to store that value, I need to hit this button down here that says STO right above the on button. When I hit that, it gives me answer arrow. And then I'm going to put the variable that I want to store it as. So I guess I'm going to hit the blue key, right? The second key. And I'm going to store this as, sorry, not that one. Not the second key, the green key. Green key to give me the alphabet. So I'm going to store that as A. When I hit enter, it's just going to give me back the number. But now if I hit alpha A and hit enter again, notice it says that A is equal to that number. So this is one way that you can store the number. And then anytime that you want to recall it, well, then just hit alpha A and then say plus, and then put in the next piece. So it's 2 times 4/5 times sine of 5/4. Okay, I get a new number. Then I'm going to store that one as A and just keep repeating this. And I suggest doing this because you see how many parentheses I have in just this one piece. If you sit there and try to do this all 9 terms with the correct amount of parentheses and everything in the right places, you're going to have trouble. So again, I'm going to hit the STO button, the alpha button, and A again. So now A is the 2.35. So take a minute or two. I would like you guys to calculate this. And someone please give me a number.
I got 7.2187022454.
Is that for everything in the brackets or the entire calculation?
Oh, that's just for the brackets.
Okay, so go ahead and divide it by 8 then. Right, because it's 1/4 divided by 2, that's all 1/8.
Yeah, so that gives 0.90233778067.
Okay. That looks pretty good, right? Because my answer up here was 0.90256. And this is 0.90233. So it's not bad. It's at least accurate to 3 decimal places. So that is using trapezoids, right, as an approximation. We now need to do this using Simpson's rule, which is parabolas. So that would be S sub 8 that's going to be delta x over 3. Again, plugging in all the same values, but the coefficients are different now. So the only benefit to have typed it all in at once is that you could go back and change this 2 to a 4. And then leave this one as a 2. All right, so I would just change these. Actually, let me just do it up here so I can save some room for myself. This would be 4, 2, 4, 2, 4, 2, 4, and then 1. So could someone else give me a number for that one? Anybody get a number yet?
I got 0.9167.
Somebody want to second that? It's close, but I think it's going to be 902 something again. Maybe you truncated somewhere. That means you cut off some digits.
I got 0.9025687.
902.5687, you said?
Yes.
Okay, so now that's good to 5, almost 6 digits, right, if we rounded. So it turns out that the parabola is slightly better in this case. The last part of the problem asks us to compute the percent error. I'm not going to waste your time doing that. It's a simple calculation, but I'll give you the formula in case you forgot it. It is the actual minus the experimental over the actual times 100%. Now, what in the world do I mean by actual and experimental? Experimental is the number that you come up with S8 or T8. The actual value is the number that came out of the FNINT function at the beginning of the problem. So for instance, you would do 902.5694 and so on, minus S8 here, all divided by the number I said, times 100%. So not a grueling calculation by any means. And it gives you an idea of how far off you are from the actual answer. Now, of course, these percentages for this problem are going to be quite low. Other problems, it might not be the greatest calculation. So there's another example here. I typically let you guys try this. We only have about 25 minutes left, so I really want to get to the next topic and at least start that. So if there's some time at the end.
Question.
Go ahead.
For the last problem, real quick, for A, so you're using the value that we calculated in the beginning, and then is E always going to be the S8, or is it, like, how do you determine whether it's going to be the trapezoid or the Simpsons rule that you use for E?
You would do a calculation for each.
Oh, okay. So we would put both for the part E. We would put both calculations.
Yeah, you would do one calculation using S8. You would do a whole nother calculation plugging in T8.
Okay, awesome. Thank you so much.
Mm-hmm. So again, how do you guys feel? Right, I know it's a lot of stuff, but there's not, like I said, there's no new calculus here, right? It's all just a simple, well, let me not use simple, but it's all just a arithmetic problem, right? There's a lot of calculation involved. So I wanted to at least start this topic so that we have as much time as possible next time to finish this, do improper, and then do some review. Granted, in the summertime, because our class goes so quickly, right, the review is not as extensive because you have a lot less time to forget the stuff. So the next topic here is integration using a table of integrals. And all of you are going to learn this technique, and you're going to say, why in the world did we just spend the last couple days learning how to integrate when I can just use this table? Well, the answer to that is, sure, when you leave this class, you may use this table whenever you want. But, in order to pass the class, you got to prove that you can integrate before using the table. So again, there are problems that our techniques cannot solve, and using those approximations, it's not always the most fun way to do things. And so another thing that we can do is we can look up an integral in an integral table. So if you go to Blackboard, I have put up a table of integrals for you. I did that, I think, right before class. So I'm just going to open that guy up. And I will share him so you can see what I'm talking about. So this is the table of integrals. And this came right out of the back of the textbook that I used from the course. And you'll see that it's got a lot of basic stuff here, like the integral of u dv. Notice that's our integration by parts formula. It's got the integral of du over u. It's got integral of secant squared. Things like integral of secant. It's got our arctan formula right there that we needed earlier. All right. Then it's got more complex forms involving the square root of a squared plus u squared. It's got a squared minus u squared minus a squared, a plus bu is the next section. And then it gets to trig forms. So notice it goes all of the squares, all of the cubes. And then once we get past cube, then we have to start using n. So the nth power of sine and cosine and so forth. There's our formulas for the mixed arguments, right? Sine of AU times sine of BU. All right, so there's a nice thing for that. So there's a lot of great integrals back here. These are ones we don't see as much, but we're going to deal with them a little bit. Hyperbolic functions. So tons of integrals back here. So what our task is to take the integrals in this worksheet and make them look like something in that table of integrals. So unfortunately the numbers here don't match up with that table, so I still have to change those. But let's just look at an instance here. So the first one says you've got the square root of 9 plus x squared. I believe that's close to the quiz problem that I gave you. I think maybe I gave you 9 minus x squared. So that we can find in the table of integrals. And from this, or the table that this was taken from, it was number 29. And notice it's got forms of x squared plus or minus a squared. So that fits this equation that's up here. And so all we would really have to do is figure out what a is and plug it in. So in this particular problem, a is 3. So down here, you notice you've got 1/2 x squared plus a squared. That would be 9. And then you have a squared out here. Again, that's 9. And then plug in a there. So that's it. You just have to find a and plug it in. But they're not always that nice. They don't always appear exactly like they would in the table. So instead, you might have to do some kind of adjustment to the problem. So that's this example here. So we've got integral of 3x over square root e to the 2x plus 1. Now I know I very briefly went through that table with you, but I can tell you that nothing in the table looks exactly like that, right? Even when you go to exponential forms. So we have to make it look like something in the table. So let me just go ahead and jump back to the table real fast. So as I said, there's a section that says exponential forms. So let's find that. So here's our exponential forms. And nowhere do I see something that's got e over the square root of stuff, right? So it's not directly in the table. So let's go back now and say, okay, what can I do to this integral to make it look like something in the table? Well, if I break this e to the 3x up into e to the 2x times e to the x, right, that's an exponential rule that says if I multiply same base, I add the exponents. Well, I can do that in reverse. And then I make a u substitution. I say let e to the x equal u. Well, then e to the 2x then, right, e to the 2x is really e to the x squared, so that's u squared. So then we get this integral. That can be found in the integral table. So we're looking for u squared, square root of u squared plus something. So we need the u squared plus something squared form. And then we look down through here and say, do we see one that's got, hey, look, there's u squared over u squared plus a squared. So that is then the form that we're looking for. And all we would have to do is plug in a and u. So let's try a few more here. It says use the table of integrals to solve the integral. Well, sine to the fourth is not directly in that integral table. So sine, that tells me to look for the trig forms. So I'm going to go there. Okay. So here are the forms that are trig forms. And as I said, there's sine squared, there's sine cubed, but after the cubes, you have to use the nth power. So for this first problem, we have to start with number 73.
I have a question. So would it still work if you split it up into 2 sine squares and did it that way?
So remember, if it's sine squared times sine squared, that's, you cannot break that into 2 separate integrals. So I think what you're trying to ask is, could you do this? Of course, that's an assumption, but that's what I'm taking from what you said. But that is not equal.
Okay.
So I'm trying to pull up both forms here so I can see them both at the same time. All right. So I want to use the form here which says sine of u, or sine to the u, or n, sorry, of u du is equal to so that's the first form that I have to use. So for my problem, n equals 4, u equals x. So I just need to plug them in. So 4 minus 1, that's going to be cubed. So if I make all those substitutions, I end up with another integral, which is sine squared that I can also get from my table. So the table I gave you, sine squared, is number 63. So I think this one was 73. Now we're going to need number 63. And it says sine squared u du is equal to 1/2 u minus 1/4 sine 2u plus a constant. And we've done that one before, right? That's just a basic trig integral. The sine squared would get changed into the power reducing formula of 1/2 1 minus cosine 2u. And that then would easily result in what we see there. So I'm using this for this integral. So the minus 1/4 sine cubed, all that stuff comes along. Again, in this problem, u is translated to x. And then you could multiply this in. Not necessarily super important. I guess I'll just write it real quick. So again, this is not overly difficult, right? I'm not really doing much calculus on my own. I just need to find the correct form in the table. Now, of course, this one is directly in the table. And again, interest of time, I'm going to skip B for now, and I want to get to C.
Are you going to give us the ones we need for the test, or we can have that integral paper for the test?
For the test, if I ask you a question about table of integrals, I typically will either give you what you need, or I'll give you like a list of 5 of them and say figure out which one you need. Because if I let you use that table, you will never integrate anything on the test. You'll just try to use the table for everything. And I don't mean you specifically. That's what I've seen in the past. Is that when I give the test, people just go, "Oh, look, it's number 25." And I'm like, "Yeah, but I said integrate. I didn't say use table of integrals." So it's just a mess if I give you that.
That makes sense. Thank you.
All right. So C looks like absolutely nothing that you've seen so far. And if you were to scan through the table of integrals, you wouldn't see it there either. So we've got to change it around somehow to make it look like something in the table. So I notice there's something plus tan squared up here. So I'm guessing I'm going to have to make some substitution for tangent. And the reason I have that thought is if we go to the table and we look at these trig problems, right, there's none of these that have square roots of trig functions squared, right? So that means that I'm stuck with the forms above that have square root of something squared plus a function squared. So it looks like u is going to have to equal tangent. So if I go back to the problem now, if tangent is u, what does du have to be?
Secant squared.
It would be secant squared dx, right? Do we have secant squared in there? I don't necessarily see a secant squared written there, but 1 over cosine squared is equal to secant squared, right? So I could rewrite this integral just like this. And then if I make that u substitution, it now looks like that. And that is a very simple form given in that table. Right, that's just a squared plus u squared, where a is going to be my square root of 5. So we're going to use number 21 that says the integral of a squared plus u squared is equal to u over 2 square root So again, I'm reading that right off the table. And once you get there, you're basically done. You just got to plug in the correct values. So in our case, u is the same thing as u, right? Because u squared and u squared are the same. But we've got 5 equaling a squared. So we have u over 2. And let's go ahead and just skip the next step where we don't care about u. We want to get back to our original. So this would be tan of x over 2. A squared is 5, and u squared is tan squared. So again, everywhere I see a squared, I'm putting 5, and everywhere I see a u, I'm putting tangent. So that looks like a pretty ugly answer. Right? Probably would have taken quite a bit of time to integrate that otherwise. Again, once you got it to this form, you could have used a trig substitution. So when you go to practice for your test, a good thing might be to get it in the correct format, solve it using the table, and then if you can solve it using another method, do so to practice, because you know what the answer is supposed to look like. All right, I think maybe I can do one of these two really quickly. And then we can come back to it next time. Let's see. I guess I'll do E real quick. So we had another problem earlier where we had E's. And it looked like we let U equal E to the X, which means U squared is E to the 2X. And so this is going to be, I'm going to break that E to the 3X into E to the 2X times E to the X, just like I did in that earlier example. And the reason for that is if I let U equal E to the X, or if I make a, well, I would make a U substitution, so maybe I should have picked something else here. Let this be Z. So now I want to let U equal this. Du is going to be 2e to the 2x. Is that what I want to do? I think actually saying it be e to the x is going to do the trick. Let's try that. So I broke e to the 3x into e to the 2x times e to the x. I let z equal e to the x, which means z squared is e to the 2x. And I took the derivative of z, or the differential, which was dz, and that's just e to the x dx. So I have that with this one and this one. That's why I broke it up originally. So that's all going to become dz, and left behind would be z squared, and that would be z squared. So now the question is this guy in the chart? So we're looking for something that looks like u squared times the square root of, we had u squared minus a number. So we need to find the square root of u squared minus a squared. I think I accidentally skipped over it. There we go. U squared minus a squared. And then we need a u squared outside. Hey, look at that. Looks like number 40. So I'll go ahead and just write the solution here. We can go over that one again if you guys like next time. So let's see, it's u over 8. U is equal to e to the x. All right. So sorry I went over a little bit there. That's the solution for that guy. So next time I think what I'll do is maybe let you guys work the first 30 minutes on some of these problems on your own. Then we can do improper integrals, and then we should hopefully have about an hour left to review. So I'm going to put up the review today. I will give you a quiz on partial fractions. Actually, I'll give you partial fractions, and I'll give you Simpson's or trapezoidal rule. So we can get two of those out of the way, and you can determine whether you're doing them well. So next time we'll finish tables, improper, review, and then on Thursday you have your test. Any questions, concerns, things you need from me before I clock out for the day?
So there's no quiz tomorrow.
I'll still give you a quiz tomorrow because you haven't finished the table of integrals, so I can give you one for that and for improper.
And what did
And
you
that'll be
say?
on guided notes number 5.
The quiz today, the quiz is going to be on partial fractions and the beginning of this one, the Simpsons and trapezoidal rule.
Okay. Thank you.
Anything else? All right, if not, enjoy the rest of your day. I'll put up those quizzes, and I'll see you guys tomorrow. Feel free to email me if you have any questions.
Thank you.
Yep.
Thank you.
Have a good day.
You too.
Thank you.
Bye.